Good morning, everyone. Thank you for watching this demo. This is the second demo or recitation for the deep learning class this fall. And today we'll be talking about backprop, which is short for backpropagation. Let's recall our three-step recipe for machine learning. There are three components of it. The first is a model, which takes in data and makes predictions. The second component is a loss function, which measures how good our predictions compare, or how well our predictions compare to the true output values that we want to learn. And finally, an optimizer. Now, the optimizer allows us to update the weights of the model to improve the loss function. And this three-step recipe is very important for machine learning and deep learning in general. Today, we'll be talking about the interplay between all three of these, in particular through the lens of the optimizer. The optimizer that we use in deep learning is basically always gradient descent, where the gradient descent that we're computing is on the loss function, which is itself parameterized by the weights. And the goal here is to minimize the loss function. Typically, that corresponds to getting predictions that are closer to the true output values that we want to learn. And we do that by updating the weights in our models so that the loss decreases. How do we know how to update these weights? Well, we compute the gradient of the loss with respect to the weights. Let's go through an example with this image. Here we have a general neural network. The input is a set of neurons on the left, and we pass these inputs through two hidden layers in this case. It could be more, where in this case, we have a fully connected layer. So every neuron in the intermediate layer is connected to every neuron in the previous layer. And we repeat this process. Remember, the way that we get one of these neuron values is multiplying the input value on the left by the weight associated with the edge connecting them. And repeat this for each one of the neurons in the previous layer. We add it all up, we apply an activation, and then we get the new neuron value. Then we repeat this process to go from the first layer to the second layer, and again from the second hidden layer, in this case, to the output. Now, the output of this neural network is the thing that we want to be the good prediction. So in the first example, we saw some MNIST data set where we had images and we wanted to predict the class that these images belong to. In that case, our output was multidimensional, but we could also think of our output as one-dimensional. It's some real value that we want to predict. And we get that by applying these weights and biases to the input to our model until we get some output value. Now, this output value, at least in the very beginning, should be completely random. There should be no learning that has happened at all. So if we put in an input, we get some random output value. The reason we have a loss function is to tell us how good is this output value, and in turn, allow us to make it better. So in this case, we go from having this output to computing some loss as a function of that output and the true data that we're trying to predict. Now, one way of thinking about the gradient, really the gradient is a higher dimensional version of a derivative, and each entry in the gradient vector is the derivative of the loss function, this thing at the very right, with respect to every single one of the weights in our network. Here, the weights correspond to the edges, and I've colored them to indicate what the relative magnitude and sign of each one of the derivative is. So for example, consider one of the dark blue lines. In this figure, that indicates that if I increase, let me get this right with what I wrote in the notes. Bold blue. Yeah. So if the derivative with respect to some weight is positive and large, it's a bold blue value. We know that if we increase the weight, we get a big increase in the loss function. So that's what this dark blue value means here. The light blue value would mean if we increase this particular weight, then we change the value at the next neuron, which in turn changes the output, which in turn changes the loss function. And if we increase the light blue value, then we get a moderate increase in the loss function. Now, because our goal is to decrease the loss function, the obvious thing to do for these blue weights is to decrease them instead. And a decrease will correspond to a decrease in whatever neuron value is associated with the thing that comes next in the network, which will in turn change the output value, which will in turn decrease the loss. Now, the same thing is true for the dark green and light green lines. Each one of these corresponds to weights whose derivative of the loss with respect to each one of these weights is negative. This means if I increase one of the green lines, then it'll change the neuron value at the next step and in turn change the output value and decrease the loss function overall. Because our goal is to decrease the loss function, I want to decrease these weights. Formally, I'll write this out, and I think you've seen this before. So let d sub L or dl dw be the derivative of the loss function with respect to some weight w. Then the update that we're going to perform will be to change the value w so that it gets the new value, w still, minus some learning rate, which I'll call alpha, times dl dw. And this is the right thing to do. If dl dw is large and positive, that means increasing the weight increases the loss function. So we want to decrease the weight so as to decrease the loss function. If dl dw is negative, this means increasing the weight decreases the loss function. Then we're subtracting a negative value, which is the same thing as adding a value to the weight, which will decrease the loss function. And recall our goal through all of this is to decrease the loss function because this corresponds to learning the data and learning the function that we care about. This is a little bit abstract, so let's try to make it concrete by considering a particular scalar example, which you may or may not be familiar with now, but hopefully this will be a slightly different way of looking at it. So we'll have linear regression. Our data will consist of two values, a single value x and a single value y. Both of these are real numbers. And our goal is to build a function so that when we input x, we'll get out a value y. Now the parameters of our function we'll call w and b. This is the weight and this is our bias. And then the particular function that we'll be using is y prime equal to w times x plus b. Now our goal is for y hat to be as close to y as possible. A natural loss function for us to use is if we define the loss function L equals y hat minus y squared. So this would correspond to the L2 loss in general. And this just means that we take the difference between our predicted value and the true value and we square that. And if this value is large, that means that we're inaccurate, our predictions are wrong. And if this value is small, that means we're making accurate and good predictions instead. Typically, we're going to define the loss function parameterized by its weights and biases. So here I'll write the loss function as a function of w and b. And this emphasizes that y hat depends on w and b. So in this case, I'll just substitute in wx plus b for y hat, which gives wx plus b minus y quantity squared. And this will be our loss function. Now, the thing that we talked a lot about in class, and which is the key to optimizing any loss function, including this very small scalar example, is if we compute the gradient, or in this case, just the derivative. So here I'll say that the derivative of L with respect to W, let's compute this quantity. By the chain rule, this is equal to 2 times the inner quantity, this, times the derivative of that inner quantity with respect to the particular weight, dw. So let's compute the derivative with respect to w. When we do this, we just apply the chain rule. The exponent comes down into the 2. We keep the thing inside that exponent. And now we're multiplying by the derivative of the thing inside that parentheses with respect to w. B doesn't change with respect to W, Y doesn't change with respect to W, but WX does, and the rate that changes is. So this is simply equal to 2 times WX plus B minus Y times X. Let's do the same thing and compute it with respect to the bias B. So I'll just copy and paste. And I'm now computing the derivative loss function with respect to the bias. Now, the same thing is true before we applied the chain rule as we did previously, but now we're computing the derivative of this term with respect to B instead. WX doesn't change as a function of B, Y doesn't change as a function of B, but B does, and the rate of change is 1. So this is simply equal to what we had previously multiplied by 1, which is the same thing itself. Okay, so why is this helpful? Well, in this particular small example, we've been able to build a model. This is the thing that we care about, and this is the first step of our recipe. We're able to build a loss function, this is the second step of the recipe, and now our job is to build an optimizer, and the optimizer will update the weights based on their derivative or gradient. So we're able to calculate the derivative and the gradient, so now we can update the weights. Let's see all of this in code. Oh, and this image right here is exactly what's going on in this case. So my network now is very small. I take in a single input X, I multiply it by W, and then I add it to 1 times B, the bias term. This gives me this Y hat, or Y prime value, which is WX plus B. Then I also compare Y hat to Y, and I get this loss function. And the thing that we care about is updating these weights in the bias so that we reduce the loss function and make Y hat closer to Y. That's what we're going to do. Let's set this up. The first thing we'll do is define some data. For fun, if you want to try this, you can set these values to anything. Here, let's say I'll set X equals to 5 and Y equals to 7. And our goal is to build a model so that we can, using a weight and a bias, we can take an input of X and get out a value of Y. The other thing we need to do is initialize our model. Here, I'll initialize it with a random number. Before we do that, let me import what NumPy, which I'll be using to generate that number, random number. So I'll import NumPy as NP. And I'll generate this random number as W equal np.random.normal. If I don't give it any arguments, it'll generate a random number between or with mean 0 and variance 1 from a normal distribution, and the size will just be a single scalar value, which is what I want here. I'll repeat the same process and generate another random normal value for the bias. Let's take a look at what W and B are. And these are random values, which are sometimes negative, sometimes positive, and seem closely concentrated around 0. Okay, so this is our initial model. The first thing that we're going to do is write some code to make our prediction. So we'll say def predict, and the thing that we'll take in for this is X, W, and B. And remember, our prediction is equal to X times W plus B, and then we'll return this value, which is Y prediction. Let's call this function on the values that we initialized so far. So if we call this function, the prediction that we're getting is 1.1, which is pretty far off from the true value that we care about, which is 7. So we need some way of first defining the loss. Here, we're going to define the loss function. I'll say it's get loss, and it's our Y prediction and our Y value. The loss will just be Y, our prediction minus Y squared, and then I'll return this value. In this case, I'll call this value Y pred, and maybe we could print out Y pred so we can see what it looks like. So it's 1.101. Let's compare that to our true value and see what our loss is. So our loss is equal to the loss between Y pred and Y. And if I print this loss out, this should be a large number, around 36. And that's exactly what we get. we get a large loss value, and this corresponds to the fact that our prediction is far from our true initial value y. How do we update this? Well, we do our optimization step and implement our optimizer. That's our third step of our three-step recipe. And let's do that right now. So we'll write all of the training code here. And the first thing we'll do is specify the number of epochs that we're going to train for. We can start at 10 and see how it goes. Now we'll have a for loop over each one of these epochs. So for epoch in range num epochs, we'll take an update step. The first thing that we should do is get our prediction. Our prediction will be equal to predict. I'm just using the function that we defined above, x, w, and b. Now we can compute our loss value. Our loss value is get loss of y pred and y. Now we're going to do the optimization step to update the weight and the bias. And to do that, actually, we'll need to write one more function, which is get gradient. When we get the gradients, we'll pass in x, y, w, and b. And we'll do the exact same thing that we did earlier, that we did analytically. So we'll write down this value as the derivative of our loss with respect to w, and this value as the derivative of the loss with respect to the bias b. First, we'll compute our prediction. So y pred is equal to predict x, w, and b. And then we know that the derivative dl with respect to w is equal to 2 times y pred minus y. Maybe I'll copy this up here, so it's easier to write out the code down here. So I just wrote down the first part. It's our prediction minus y times x. Now the derivative of the loss with respect to b is equal to the same thing, just multiplied by 1. Okay, and our gradient is just the fancy word for a multidimensional derivative, and this will be a vector, which I'll form like this. So it's dl dw, dl db, and I'll return the gradient. Okay, so in our optimization step, and maybe we could call this function right now to see what we get. So get gradients x, y, w, and b. And we get a very large gradient for the first value. So we get minus 58 and minus 11. What this tells us is if I increase the weight w by one value, then the loss will decrease by a factor of minus 58. Similarly, if I increase the bias by a value of 1, then the loss will increase by a value of minus 11. So it looks like the right thing to do here is to add a small value to the weight and to the bias, and we'll accomplish this by subtracting the gradient, which is negative. So we're adding a positive number to each one of the values here, which is the right thing to do in this case, as we know analytically. So let's actually go through the code to do this. The first thing we'll do is get gradients x, y, w, and b. And I'll put this in something called gradients. Now we'll update the weight. How do we say we're going to update the weight? Well, we're going to say the weight is equal to the weight value minus alpha, which is this learning rate. I haven't defined the learning rate yet, times the gradient of the first of w, or with respect to w, which is the first value in this list. So I'll say that's gradient 0. Similarly, when I update the bias, I do bias equals b minus this learning rate factor times the second thing in this list, which is the gradient with respect to b. Now it remains to define this learning rate. Let's start the learning rate at a value like 0.01. And also, I want to print out the loss as we go to see how we're doing. So if I just run this value, it looks like we're doing really well. So off the bat, we started with a large loss, 34, and we went down very quickly to a smaller loss and an even smaller loss over time. And we're getting something that's very, very small within 10 epochs. Now, let's say that I didn't know to set the learning rate to be 0.01. So I'll just reinitialize our model by setting new values of W and B. And I set this instead to be a value of 1. If I run this instead, I get the exact same code. It's just the only thing that's changed is the learning rate. Now I start with a large learning rate, but immediately I'm going in the wrong direction. So the next value is very large and the next value is very large, and it gets bigger and bigger and bigger. The reason this is the case is because I have these very large gradient values and I'm adding the very large gradients to my X and W values. And in doing so, I'm making them way too large, which is a problem in this case. So generally, a tip is that if the loss is behaving strangely, so this means going up or oscillating, try decreasing the learning rate. So in this case, maybe we'll try a value of 0.1 instead, and I'll just reinitialize the model so we're starting from decent values. Now, if I run this again, it's not as bad as it was before, but it's still not great. The loss is increasing over time, which means if we follow this tip, it's still going up, it's behaving strangely, we should try decreasing the learning rate again. I'm decreasing the learning rate by a factor of 10, which is generally pretty standard in deep learning. I'll reinitialize the model and I'll repeat this process. And now that I have 0.01, it looks really good. The loss is going down. We might say, okay, what if we try decreasing the loss again? I'll reinitialize the model and I'll run this process again. Oh, maybe I didn't reinitialize the model. Okay. If I run this again, it looks like it's not decreasing very quickly. It started large and it's decreasing by like 10 every turn, which is not so good. Which leads us to the second tip, tip 2. If the loss is decreasing slowly, try increasing the learning rate. So here I will increase the learning rate and I'll reinitialize the model. And let's see what we get. We get excellent performance. So the process that we just did is called hyperparameter tuning. Notice that we didn't actually change any of the code here, any of the code for learning. The only thing that we changed is this learning rate, which we call a hyperparameter. Choosing the right learning rate is something that's very important, as you saw, because if we chose something that's too large, we get really bad error. If we chose something that's too small, we don't get much learning or improvement whatsoever. So it's important to choose the learning rate to be the appropriate value, and you can tune it by trying different values of it. So I'll say this is hyperparameter tuning, which is very important. Okay, so what have we seen so far? We've seen a scalar version of a neural network, and we've seen how to implement this backpropagation step so that we're computing the derivative of the loss with respect to each one of these weights and biases, and updating them accordingly so that our model will learn. Of course, this is a very simplified neural network because we only have one input and we only have two things that we change, one weight and one bias. And it's also simple in another way because we're only trying to fit a single data point, the example 5, 7. Now, of course, using calculus and convex optimization and setting the gradient equal to 0, you could have just found the exact values for W and B. But in general, that doesn't work when the neural network is very complicated. So let's see an example, also of linear regression, where we have more weights, so more input parameters, and we also have more examples that we're trying to fit. So I'll call this multivariate linear regression. In this case, this is what our model looks like. We have 3 inputs this time, 3 corresponding weights, and a bias term. So this is our multivariate example. And let's define what we mean by our model and our loss function. Okay, so in this case, our data will now look like a matrix. So our data consists of a matrix X, which is, I'll say, in the real numbers. And the dimension of this matrix is n times d, where d here is the number of features we have. So for example, we'll just set these values to nice things at first. So we'll say n equals 10 and d equals 3. This corresponds to the case that we have 10 data points and 3 features as described in this image. And we're putting all of that into a matrix where each one of the rows corresponds to a single observation of the number of columns, which in this case is the number of features, which is 3. Now, this is our input data. We also have our corresponding output that we want to meet, which is y. And y is a single real number in this case. It's an n-dimensional vector, so it's a single value for each one of the corresponding inputs. What does linear regression look like in this case? So our model is, I'll use the same notation as before. It's y hat equals x multiplied by some weight vector w plus some bias term b. Let's make sure that the dimensional analysis on this is correct. So y prime should be an n-dimensional vector because we're going to compare it to an n-dimensional vector, which means the thing on the right should also be an n-dimensional vector. B is a single real number in this case. So what we need to do is multiply it by the all ones vector. I'll call the all ones vector this fancy version of a 1. Oh, which I guess doesn't show up. Maybe this works, yeah. So I'll use a bold 1 to indicate that this is a all ones vector. I'm multiplying it by b, and the dimension of this is n. So that's now correct. Let's make sure that this is also n-dimensional because we'll be adding it to an n-dimensional vector. Well, n, or x, is n by d dimensional, and the weights, the number of weights that we have in this case, is also just the dimension d. So we're multiplying an n by d dimensional matrix by a d dimensional vector, which should give us an n by an n dimensional vector. So we do dimensional analysis, and the only tricky part here is that an n times d dimensional matrix multiplied by a d-dimensional vector gives an n-dimensional vector, and this should be review from linear algebra. So indeed, this model makes sense, and we can check it with our dimensional analysis. The thing that we want on the left is an n-dimensional vector, and that's what we get from the thing on the right. Now let's talk about our loss function. Our loss function in this case, should also be the difference between y hat and y. So we could write L equals y hat minus y. Here though, we can't just square this. Why not? Well, because these are two vectors, so we can compute their difference. That's the difference of each term, but then it's strange to mean, what does it mean to square a vector? The thing that we'll be doing instead is taking the L2 norm of this, which is the natural variation of what you'd expect. We sum up over each one of the entries, so that's I equals 1 to n of y prime I minus y minus yi. We square that value, and this is equal to, oh, let's put this in the text. This is equal to the loss function. Again, I just want to emphasize that this is a function of w and b, because the reason that we know that y, or what y hat or y prime is a function of w and b. So if we want to decrease the loss, the things that we have available to us are to change the vector w and change the vector b. And that's exactly what we're going to do. Let's start off with the same thing we did previously, which is, I'll put this figure above, which is initializing our data. So I'll say n is equal to 10, d is equal to 3, and I'll define a matrix, which is random normal because that's easy to generate. And here I'll specify that the size is equal to n by d, which should be a 10 by 3-dimensional matrix. And I'll also specify that we're going to build a vector that we want to predict y, which is random normal, and its size is equal to n. When I run this code, let's inspect that it works. So I'll say I'm printing x, let's print x's shape, and let's also print x, and we'll do the same thing for y. So I'm printing y, I'm printing the shape of y, and I'm printing what y is. If I do this, I get exactly what I want. X is a 10 by 3-dimensional matrix, so there are 3 columns and 10 rows, and all of these values look like they were generated from a normal distribution. Similarly, Y is a 10-dimensional vector where all of the entries are also generated from a random normal distribution. And the idea is that I want to come up with some weights so that when I multiply the first weight by this, and the second weight by this, and the third weight by this, and add a bias term, I get a value which is close to the thing that I want over here. And I want that to be true not just for the first row, the first one of my observations, but for every single one of them, all 10 of them. How are we going to do this? Well, we're going to build a model. So I'll say initialize our model. Our model will consist of W. W is a vector, and the dimension of W has to be D because I'm multiplying each entry here by the corresponding W value. So the size of this is equal to D. And I'll also have a bias term, which is just going to be a single scalar real value. Let's print out what these are so we can confirm that it makes sense. I print out W, I get a 3-dimensional vector, 1 for each one of my features, and I print out B and I get a single scalar value, which is the bias term. As we did before, let's define the same functions, predict, loss, and gradients so that we can do some deep learning on this. The get prediction function will be defined similarly. So it's we def predict, we're going to take in capital X now, our W and our B values, and our prediction Y pred is going to be what we defined up here. It's going to be X times W plus B. In Python, you can use this at value to mean matrix multiplication, and I'm adding B, which is a single number to it, but implicitly, if the dimensions don't agree, NumPy will realize that when I'm adding a singular scalar value to a vector, what I really mean is add this single scalar value to each dimension. And let's test this function out. So if I predict on X, W, and B, and I'll call this Y pred, and then I print out our prediction Y pred, I should get something which initially looks very random. Let's compare this to our actual thing that we want to get, Y. So this is -2, this is like -0.3, this is 0.14, this is -0.39. Generally, these numbers don't agree at all, which we wouldn't expect for them to because this was randomly initialized, and our model at this point doesn't do anything special. It just applies these random weights to X, and it gets out some prediction. Now, this is the first step of our model. We get, or our recipe, we get a model for this higher dimensional case. And the second thing that we should do is get a loss function. Get loss function. Here we'll call it the same thing, and it'll take in our prediction Y and our the true value Y. So our loss here will be Y pred minus Y. And remember, we square, this is a vector. We square each one of the entries in this vector, and then we take the sum of it. This itself will be a vector, so I can just call sum here, and I'll return this loss value. Let's see how this works in practice. So if I say loss equals get loss, our prediction, Y pred that we defined above, and Y, and then I print out our loss, I should get a fairly large value, which I do, 37. So there's a big difference between what we're predicting and the actual value that we want. How do we improve this? Well, we do our optimization step of our 3-step recipe. That means that we'll need to define a function to get the gradients. Okay, now we need to do a little bit of thinking because it's not immediately clear when I take the derivative of this with respect to W, what does that mean? Because now I'm doing matrix multiplication. Well, it turns out that gradients, everything generalizes nicely to a higher dimension. So if I want to compute the gradient, remember the gradient is a vector for each weight or bias where the entry in a dimension corresponds to the derivative of the loss with respect to the weight or bias. And instead of writing dl dw, I'm going to use this new fancy notation, which is nabla. This is the notation for a gradient. So it's a gradient with respect to w of L. This generalizes very nicely to what we would expect from the scalar one-dimensional case. If I take the derivative of this function with respect to w, I can just apply the chain rule to it. And let me specify what this function is in terms of w and b to make this more clear. And I need to subtract y here. So I can just write this loss function. Maybe I'll put it on another line. As this. So the loss function is the difference between the prediction and this y value, but now these are higher dimensional values, and this is an L2 norm. You can prove this to yourself by using the summation version of this definition, or you could take my word for it. But the higher dimensional gradient with respect to the weights performs very similarly to how we'd expect it to perform using our intuition from the scalar case. So we apply the chain rule, and that gives us 2 times the thing in the middle. That's the difference between this vector. And now we have the same thing we had before, where we're applying the nabla now to the thing that we have in the middle, which is this quantity. Intuitively, b doesn't change with respect to w, and y doesn't change with respect to y, but xw does change with respect to w, and the rate that it changes with respect to w is x. Now, this is kind of a funny statement because x is a matrix, but we know that we need to multiply by a matrix because that's the rate of change of w. It's just unclear how we need to multiply by that matrix. To do that, let's do some dimensional analysis. We know that the thing on the left, this has to be a d-dimensional vector because there are d weights, and each entry in this vector corresponds to the derivative of the loss with respect to the corresponding weight. So it better be the thing on the right side of this is also going to be a d-dimensional vector. So far, that doesn't look so good based on this term because we know this is an n-dimensional vector. The one vector is n-dimensional, y is n-dimensional, and x times w is n-dimensional. So we need to multiply by x in such a way that we turn this n-dimensional vector into a d-dimensional vector. And it turns out that the answer here, I'll put this on a new line, is to multiply by x transpose times the thing that we have here. So we know that we're multiplying by x, it's just we need to multiply by x in such a way that we get a d-dimensional vector out of it. And this makes sense because we have x is an n by d dimensional matrix. So x transpose is a d times n matrix times a n dimensional vector. When we do this, we get a d-dimensional vector out, which is exactly the right dimension for this gradient. So that's the gradient of the loss with respect to w. Let's compute the same thing with respect to the weight b. So I'll say, let's copy that. The gradient with respect to our bias b is simply the same thing by the chain rule, but now the gradient of this thing with respect to b. This doesn't change as a function of b. This doesn't change as a function of b. The only thing that does change as a function of b is this term, b times the all ones vector. The rate that it changes at is the all ones vector rate. Now we can repeat the same process of doing multiple dimensional analysis because we know we need to multiply by the all ones vector somehow. The way that we need to multiply by it is so that we can get at the end something that's one dimensional, because this nabla b L vector, this gradient with respect to b of L, has to be one-dimensional because there's only one bias in it. So we need to somehow multiply by the all ones vector so that we turn an n-dimensional vector into a single scalar. And we can do the same thing that we did before, where we transpose our all ones vector and we multiply by it on the left. And this thing times that gives us this quantity, which is really the sum of this vector. And the dimensional analysis, again, makes sense because we know this is n-dimensional and this is n-dimensional. So if we do a 1 by n-dimensional vector times an n by 1-dimensional vector, we get out a single vector of dimension 1 or a single scalar, which is the right dimension here. So let's implement all of this in our code. I'll copy this down here so it's easier to refer back to. And we'll compute our gradients here. So we'll define a function which is get gradients, and we'll take in x, w, let's say x, y, w, and b. And we'll get the gradient with respect to w first. How do we do that? Well, we'll just copy what we found out on this line. So that's x dot t, this transposes x, multiplied by the matrix 2 times parentheses x times w plus b minus y. And we can repeat the same process of copying what we know is true for the gradient of b. This is simply, instead of multiplying by the all ones vector, I'll just sum up this vector, which is the same thing. So this is 2 times x multiplied by w plus b minus y. And I'll take the sum of this whole thing. The same way, and then what I return is gradient of w and gradient with respect to b. We can compute the gradients for our initial example, y, w, and b. Oh, and it looks like we're running into an error, which is the input operand 1 does not have dimensions. Get gradients, gradient w, x transpose. Okay, so let's make sure that everything is defined up here. So we have x is 10 by 3, y is 10, w is 3-dimensional, and b is 1-dimensional. And it looks like input operator 1 does not have dimensions. Okay, so when we run into an error like this, we can try to step through and see what the issue is. So let's do part of this computation first. I'll compute this value. If I compute this, then I know we're in good shape. Okay, so I get an array, and let's check the shape of this array. This is going to be a 10 by 1. So this is an n-dimensional vector, which is exactly what we want. Now, if we do x dot transpose multiplied by this thing, we're getting an error because I didn't add this there. Okay, we're also getting an array. So it looks like, the thing that I did wrong is that I need to multiply by the matrix and then move this scalar multiplication out here. So if I run this, I get the right answer. I get the gradient with respect to each one of these values of the weights and of the bias. Now remember, this is telling us how we need to update the weights and biases, basically how we need to wiggle them in this picture so that we can change the output that we get and decrease the loss function. So let's implement this in practice using this basically the same training code that we used previously. So I'll just copy this training code from above and put it down here. Notice that it's very cool that we can actually just copy the gradient, copy basically the same code that we used previously. This tells us that no matter what our data looks like or what our neural network looks like, the training process should be very similar. Except here, we just need to be slightly careful because we called things different values. So I redefined the predict function and I said that its input is capital X. Our loss function is also redefined. And our gradient function, instead of returning just one vector, it returns gradient w and gradient b. Now this just means that when I update w, this is a d-dimensional vector, I need to update a corresponding value for the next entry here as well. So I can multiply by gradient w, and then here I can multiply by gradient b. If I run this process, I immediately get an error, which is the int object does not have attribute t. This is because when I specified x, I didn't call it capital X instead. So if I run this process, I get a decrease in loss over time. Maybe we could say that this decrease is too slow. So I'll reinitialize the model, which just corresponds to defining new weights and biases, and I'll decrease the learning rate slightly. Increase the learning rate, because if we increase the learning rate, we expect the loss to go down faster. Looks like I increased it too much. It was a wrong thing to do, because now the loss is getting larger and larger over time. So again, I'll reinitialize the model, and maybe I'll just increase the number of iterations that I run this for. So instead of running it for 10 iterations, I'll run it for 100. And it looks like I'm able to get a small loss value pretty quickly, but it stays at 9 and doesn't really go smaller than that. Let's go back to our values up here to see how our function is doing. It looks like we're not getting very good predictions here. Why is that? Well, I think part of the problem is that we have 10 examples, but only 4 values that we can change to try to fit them better. So something we could try is changing our value of d so that we have more levers to pull, more weights to try to fit this data. If we increase d, so there are more features in our data relative to the number of things that we need to fit, then we can run this process and we can get a much lower loss value. So if we compare our prediction to the thing that we get at the end, now we're getting values that are much closer. So if we use more weights and more values, we can increase the predictive power of our function. And this is part of the reason why we have neural networks that are so large, because we want to add complexity and richness to our function class so that we can fit our data better. Okay, so what have I showed you in this class? Basically, we've done linear regression, which is a very simple model, but using very general tools for deep learning. We saw how we computed the model, the loss function, and the optimizer. The optimizer was simply computing the gradient with respect to each weight and then updating it accordingly. Hopefully, you should believe me when I say that if we had a more complicated loss function, the gradients here would get more and more gross. You'll see this on the 5th homework problem that you have on your current homework when you try to implement this process for a larger neural network where there's a hidden layer, the loss function is different, and you have a nonlinear activation. It's still possible to compute the gradient, but it's not fun. And on top of that, it can be very inefficient to calculate it in this way. The solution to this is to use something called auto differentiation, or autodiff, where you keep track of these values as you go, and it makes doing the backpropagation step very easy for you. That's something that we won't cover in this class. I decided not to do that as the current demo because I really wanted you to get a better understanding of how this process works instead. And I think that there's not a lot of value in understanding the machinery of autodiff because it doesn't generalize to other techniques that you'd want to apply in this class. I just want you to understand that computing the gradient by hand here can get very complicated and messy, and we need to do something that's smarter. If you're curious about the way to do that smarter thing, then you can go to the place where we have all of our demos. And there are 2 labeled demo 2. The one that we just went through is backpropagation, explaining the process of what we covered in this video. And the other one is autodiff, where we explain the process of computing or using autodiff so that we don't have to compute the backpropagation or gradient step in a complicated and time-consuming way like we had to today. So I'll leave this for you to peruse online if you're interested. Thank you so much for your attention and best of luck with the coming homework.